Let's be real. What? Are we supporting the fellow classmates or are we scoping out the area?
All right, let's take a look at page 173. We're going to take a look at our next section today, which is a continuation of these derivative shortcuts that we've been talking about. We don't really have any more shortcut processes. What I mean by that is there's no more like product rule, quotient rule, chain rule, like where you have to go through multiple things. Our shortcuts from here are just going to be, quite frankly, things that we have to know. Okay, that we just have to memorize. You know, when I say the derivative of sine, you think cosine. Okay, so that is a derivative shortcut. That is something that we just have to know. Those are the ones that we're going to take a look at for the rest of this unit. Okay, and in this section, we're going to take a look at exponential and log functions, like base E and natural logs. Let's not judge a book by its cover. We're thinking that this is going to be difficult, and it's actually not. Okay, I think you're actually going to like these maybe more so than some of the other ones that we've been doing. Okay, so unlike the other ones that we've gone through where I've tried to show you where the derivative comes from, I can't talk today. I'm just going to go ahead and give you the shortcut. If you are extremely interested in where the shortcut does come from, I can definitely go over that. Okay, kind of the why or where behind it. But for right now, I'm more concerned that we can kind of remember it, if that makes sense. I know that goes completely against my philosophy kind of as a math teacher because I want you to understand or see where it comes from. But for time purposes, we're going to just go straight there. Does that make sense? Okay, if you really want to know though, by all means, you can ask and we can go over where it comes from. So whenever we have a natural exponential function, that's our base of E, and we're going to take a look at two instances or two shortcuts for this example. So let's say that our function was very simple. Okay, it was just e to the x. The derivative of e to the x happens to be e to the x. It doesn't change. It's the same thing. Yeah. However, if our function is e to a function, okay, something other than x, so if you take a look at the examples on the rest of the page, you see how it's like e to the sine, e to the 2x plus 3, e to the 2x. Okay, if you have something in that power other than x, which is more often what's going to happen, this is the derivative shortcut that we're going to have to be familiar with. And it kind of comes from, or it stems from this concept, the derivative of e to a power is e to that power, but you're going to multiply by the derivative of that power. It's very similar to the chain rule. You know how we always finish the chain by multiplying by the derivative of the inside? That's kind of what's going on here. Doesn't this make sense though? If you have e to the x, the derivative would be e to the x times 1, because that's the derivative of the power. But times 1 doesn't really mean anything, so that's why it's just the same. So depending on what we have, if it's just e to the x, it remains e to the x. But e to a more complicated power, we'll have to finish by multiplying by the derivative of that power. Yes?
So does it only work when it's e?
You mean like if we had 8 to the x or something like that? That would be something different. That's something that we explore in Calc 2. Okay? Okay? So this is just going to be base e though, to answer your question. Okay? So we're going to go ahead and practice this derivative shortcut. So notice how our function is e to a power, and that power is something other than x. So we know we'll eventually have to multiply by the derivative of that power. So this is going to kind of fit our second derivative shortcut over here. The derivative of e to the sine would be e to the sine. But we got to multiply by the derivative of sine, which is cosine. Okay? Now, when we rewrite this, since these are being multiplied together, if you really wanted to, you could change the order in which things are written So just be clear that it could be written like that. Okay, but it just depends on how far you want to simplify it or where you want to go. Okay, so we'll say there's our derivative. All right, the next one. We again have e to a power, so the derivative is e to that power, but we need to multiply by the derivative of the power, which would just be 2. Okay, rewriting it, we can move that 2 out front as a coefficient, and there's our derivative. We doing okay so far? Not too bad? Okay. All right, the next one, we're going to find the derivative. We do have a coefficient of 3 out front, so we can simply keep that multiplier in the derivative. I know some of you were exploring this last week when you actually went through a product rule, but you noticed how the derivative of 3 would be 0, and that eventually wouldn't matter. So whenever you have a coefficient, you can just drop it down or bring it down for the derivative. So if we'd want to find the derivative of e to the 2x, it would remain e to the 2x, but we got to multiply by the derivative of the power, which would be 2. So in the end, this would be 6e to the 2x. What do you guys want to try for the next one? Bless you. Why? Mm-hmm. You do. You're multiplying two functions together, right? If you read it out loud, it would be 2x plus 3 times e to the 3x. So just like we discussed when we were doing the chain rule section, you might have to start using more than one shortcut to help you find the derivative. So we're going to use the product rule, but in that process, we're going to have to use this shortcut for e to the x. So let's do our product rule. We'll have 1, and then we're going to multiply by d2. So the derivative of e to the 3x would be e to the 3x times 3. Okay, the derivative of the power. So there's 1d2 plus 2, and then we're going to multiply by d1, which would just be 2. All right, so if we clean it up, we'll have 3e to the 3x times 2x plus 3, and then plus 2e to the 3x on the end. Again, you could keep simplifying. I know some of you might look at this and think that you might want to distribute to get rid of those parentheses. That's completely okay. Okay, it depends on how far you want to go, how far you want to take it. If you need to match it to a multiple choice question or not, that's a completely different story. Okay, so it just depends on what's needed for the question. What about the next one? Can we think about any shortcuts? If you read it out loud, that might help. Product, yep, we're multiplying two functions of x together. So we'll have 1, and then d2 would be e to the 2x times 2. And we got to add 2 times d1. Now, cleaning it up just might involve reordering some terms. It might look something like that. If you wanted to keep going, notice how both of these terms have a 2 in common, an x in common, and an e to the 2x in common. So we could think about factoring, if that would help us. If we take a 2 out, an x out, and an e to the 2x out, we'd be left with x plus 1. Okay, so there's multiple ways you can simplify this, like I said. Maybe you don't want to do that, maybe you have to do that, I don't know. Okay, but we got to get used to rewriting things if we have to. We sure we're doing okay? Yeah? What about the last one? Do we notice a shortcut? Chain. Okay, so we can write this as e to the 2x minus 6 all to the 1/2 power. Okay. Does someone see anything different besides chain? We could do chain.
No, you could distribute the half exponent.
Can we simplify this even further? This would be e to the x plus, or sorry, x minus 3. And wouldn't that get rid of the chain? Yeah, because we don't really have that inside-outside anymore. Okay. So you could do chain. That would be perfectly all right. You could simplify it, which is perfectly all right. There's always more than one way to do or do something. It just depends on what you notice first. So if this is the most simplified form, maybe we can find the derivative there. The derivative would be e to the power times the derivative of the power, which would just be 1. So there's our derivative. No chain necessary. But you would get the same thing if you simplified through the chain. Okay, again, depends on how far you want to take it. We doing good? We'll try another one on the back. Yeah, we'll try it. Do we notice a shortcut? Quotient. All right. We'll have low times d high. So e to the 5x times 5. Low d high minus high d low square the bottom, and away we go. So there's the initial quotient rule. Let's clean it up and see if we can make it a little bit more eye appealing. We'll have 15x squared e to the 5x minus 6x e to the 5x all over 9x to the 4th. Can we keep going? What do you see, Nish?
You can factor out an x out of the top and bottom and cancel it.
Okay, so we can definitely take out an x. Can we take anything else out? Anything else that the top has in common? Yeah?
A 3.
A 3. Anything else? E to the 5x. Okay, so that's our GCF. And then we'd be left with 5x minus 2. So it looks like 3 divided by 9 could simplify to 1 over 3. X divided by x to the 4th, we'd have an x to the, or x to the 3rd, or x cubed on the bottom. And the e to the 5x did not cancel, and neither did the 5x minus 2, so those are still up top. So there is a pretty nice simplified form. I like it. All right, e to the x, not that bad? I don't think so. All right, natural logs are going to be very similar. We're going to take a look at two different shortcuts, again, depending on which type of natural log we have. If we have the natural log of just x, okay, nothing crazy, nothing too out there, okay, just x, then the derivative is 1 over x. Do we need some lead? You're good? It's hidden in there? Okay. What does get tricky is if we want to take the natural log of a function, for instance, 2x minus 3, 3x squared plus 2x, okay, something a little bit more involved. The derivative is the derivative of the inside over the inside. And if you really take a close look at it, that basically fits the other derivative shortcut as well. Because the derivative of x is 1, and it'd be over the inside, which would just be x. Okay, so this is the most basic derivative shortcut if it's just a natural log, but more often than not, we're going to have some type of function that we're going to have to be aware of. Okay, so let's try this shortcut on a few examples. The derivative of natural log of 2x minus 3. So notice how the inside of the natural log is something other than x. We're going to have to take its derivative into consideration. So what's the derivative of 2x minus 3? 2. Okay, so that's our numerator. And then it's over the inside, which would be 2x minus 3. There's our derivative. Okay, it's not the quotient rule. I know the derivative is a fraction, but you're not doing the quotient rule itself. It's just the derivative of the inside over the inside. This is just for natural logs. Okay, the next one, again, kind of a complicated natural log because it's something other than just a simple x. We need the derivative of the inside over the inside. So that would be 6x plus 2 over 3x squared plus 2x. Simpler than we thought? Yeah. What about some trig? It's a natural log. Okay, so we need the derivative of the inside over the inside. What's the derivative of cosine? Negative sine. Can we simplify that? Negative tangent. Good. All right, how do we want to approach this last one? If you wanted to, you can rewrite it as the natural log of 2x minus 4 to the 1/2. Chain. All right, so the derivative of the inside, we'll bring down the 1/2, keep the 2x minus 4, new power is negative 1/2, times the derivative of the inside would be 2. Okay. So this is the derivative of the inside of the natural log, but we got to keep the inside of the natural log, so it would remain a square root of 2x minus 4. We're going to try to simplify it. So this is one massive fraction. Can we start moving items or simplifying things? What do you see, Nish?
In the numerator, 2 times 1/2 plus square root.
Goes away? Okay. Go ahead, Christian.
The negative 1/2 is 1 over the square root of whatever that thing in the middle is that makes it on the bottom.
Okay, so this can move to the bottom. So if this whole quantity is moving to the bottom and the 2 and the 1/2 canceled, we basically have a placeholder of 1. So not only do we have the initial square root of x, or 2x minus 4, but we're also bringing down and multiplying the other square root of 2x minus 4. So what's going to happen there?
Dude, calm down.
What's going to happen to those square roots?
Stu wants to answer the question.
Still, Addison, you good?
He has the answer.
He has the answer, just doesn't want to talk.
He just doesn't want to do it.
Maybe they don't come to speaking class.
Yeah, seriously. Get away. Probably not be
All right, the square roots would cancel, and we got 1 over 2x minus 4. Okay, so these are 2 new derivative shortcuts we're going to add to our kind of list that we've been accumulating so far. The derivative of e to the power is e to the power times the derivative of the power. And then for natural log, we need the derivative of the inside over the inside. Okay, again, this is a basic one. We're going to see this show up sometimes, but this is kind of the more meaty of the 2, if you will. Okay, all right. What we're going to do today is take a look at derivatives on our calculator, because up to this point we've done a lot of this by hand. Okay, and you are allowed to use a calculator on the AP exam, so there has to be something related to calculus that we can use to our advantage. So what we're going to do is start to find derivative values of extremely complicated functions. We could find the derivative by hand, okay, for instance of this number 1, because we went over the derivative shortcuts for e to the x and trig functions, and notice how this would involve a product rule. So you could take the time to find the derivative by hand, but your calculator can do it as well. But it can only do it for certain cases. All right, I don't want you to be, what's the word? Reliant. Good. I don't want you to be reliant on your calculator because it can only do so much. Your calculator can only find derivative values. It cannot find derivative equations. Do you know the difference between the two? Okay. We're going to find a derivative value. Notice how we're going to be plugging in a number. Okay, your calculator can do that. Your calculator cannot find the derivative equation. For instance, if you were to do the product rule, okay, it could not give you that answer. So on your calculator, if you do me a favor and hit the math button, we're going to scroll down to number 8. And do you see how it says deriv? Okay, that's for derivative. Go ahead and select number 8. We're going to type, first of all, do we get these little boxes on our calculator? Depending on your operating system, you may or may not have them. Does it look like that on your screen? Yeah? Okay. So what we're going to do is type in different values for these boxes. If our one of our notations for derivative was dy over dx, so what this notation is asking us to do is to find the derivative of this function with respect to x, which is just your independent variable. So the first box will forever and always be an x. The bigger box inside the parentheses is the function that you want to find the derivative of. So we're going to go ahead and type in 3 e to the x times sine of x. And the moment you type in x for the dx portion, it fills in the x outside of that evaluation bar. So this notation is telling the calculator to take the derivative of this function and then evaluate it. That's what the vertical bar means. Evaluate it at the x value of, we're going to type in -2. Now, since we're working with trig, you got to make sure you're in radian mode, okay, not degree mode. And we'll just go ahead and hit enter. So if you were to do this by hand, okay, go through product rule, all your different shortcuts, and then plug in -2, this is what you would have gotten, okay? But your calculator can do it quicker for you. It can find derivative values, okay, not equations. So we'll say that the derivative at -2 is -0.5381. Now that we know the derivative value, can we determine what f of x is doing at -2? How's it behaving? Is f of x increasing or decreasing or have a horizontal or vertical tangent? What do you think, Christian?
It is decreasing.
Because?
Negative derivative.
There we go. Decreasing because f prime of -2 is negative. I like it. So we're just going to go ahead and practice using this command on our calculator. Again, we could figure these out by hand because we know all of our shortcuts, but since they're a little bit more involved, we'll let the calculator do that for us. Notice how for every single one, though, we're plugging in a number. Okay, you have to have that stipulation in order to use this capability of your calculator. So, yes?
What about put right there? Like on the bottom?
X. Okay. All right, so hit math down to 8. The first box is an x. The second box is your function. And the last box is the number that you want to evaluate the derivative for. All right, 11.2681. How is f of x behaving? Increasing because? Positive derivative. All right. Let's try the next one. Math 8, x. We'll have natural log of cosine. Are we getting these numbers? Is the calculator working out for us? Yeah. All right, so for number 3, f of x would be decreasing because our derivative is negative. Do you guys think you can do the next 3? Yeah?
I can know at my calculator.
Yep.
Like, when I'm typing in the ln cosine x, I can't make it so like x squared is on the bottom. I don't like. I'm trying to move the position outside the cosine.
Type in x to the negative 2.
Do I have to do that? Well, I can't get out
I can't, you can't create a fraction.
I just put divided by.
You could do divided by x squared.
Like I
But it
can't get out of the
you
cosine.
can't get out of the cosine
It looks like
parentheses.
glasses don't work.
It's weird, it happens to mine too.
So, hold on. So
I just
type.
plugged in x to the negative 2.
You could do that. So it'd be natural log
Mine don't do that.
cosine. Yeah, let me see.
Like when I try to press out of that, I just like
Oh.
use that.
Okay, so here's the thing. So notice how you have a open parenthesis for the cosine, but then you have an open parenthesis for the log.
Yeah.
You have to. So when you close a parenthesis, that closes off the
my
cosine,
goodness.
and then you got to close another parenthesis to close off the log,
Yeah.
and then you divide by x squared.
Okay, I didn't even notice that.
That's okay?
Thank you very much.
Yeah. Is that what yours was doing, Anuj? You got to close off your parentheses. Okay? All right, go ahead and try the next 3.
Oh, that's fast.
I mean, did you figure it out? I don't see what's
What the stamp?
I literally have every single fancy open and closed. Did you calculate?
Exactly, and it still doesn't work.
Yeah, wait, what was your problem?
You have to add, you have to make sure literally all of your parentheses are
I am, like, boom, boom.
Kane.
On my version of the calculator, it tells you which parentheses, some parentheses are bigger than others, or exactly right.
Yeah, that's how mine is too, but in.
Alright, Kane's calculator's from 1980.
Actually,
Yeah, that's pretty Cisco, man. Cisco, yes, you did.
Alright, I'm just trying to figure out what's wrong.
You trying to do the I can't believe, I'm so glad I got the other calculator.
You know, I'm on this dead.
You have so many parentheses up there.
Mine's dead, but in my locker.
Okay, that one's closed. Boom, got that one. Alright, fast. Moving on. Divided by x squared. Yeah, you're good.
That's what I'm saying.
Oh, because you didn't close this one.
Which one?
You didn't close the very last one. What? The very last one over here. That's two back here. You need to delete this last parenthesis.
No, wait. Which
Yeah.
one? Which one?
The very last parenthesis, the entire thing, is closed and not open.
Do you understand how we're doing time?
No, I actually took that. I touched that.
Yeah, because it's not a real answer because it might be undefined at that spot.
Okay.
Which
How-
means
how
that
the heck
it's
do you do it on this one?
That's
So,
exactly what mine
I
is.
Math?
can get to it. Yeah.
I literally typed in like 10 times.
Oh, it's an older version. Okay. So, if I remember correctly,
Yeah, mine yielded undefined.
because you don't get the boxes,
Yeah.
you gotta type in, you know how the first one we type in on this one is an X?
Yeah.
I think that's what you have to type in here. And then you gotta separate them with commas.
Oh.
So, your independent variable is X. Your function, which one do we want to try?
Let's try the first one.
The first one?
Last time I looked at calculator.
3e to the x times sine of x, comma, and then I think you just type in -2, because that's what we'll
Yeah.
plug in there, and I'm hoping this is right. No.
Error. I
Um,
don't know how to work it. Okay, look up the owners manual.
is this your calculator?
Yeah.
Very sure we have the
See, this is how you had to type it in before they upgraded the operating system, which makes it a little bit better. It just depends on, it's the syntax, like how you need to type it in. You might have to look it up. I am not sure. Sorry.
No, it's okay.
Okay.
It's not mine. So he can fail.
It's not mine
Can you get, he's getting errors on the regular.
because it's undefined.
It's not, well, for that one, yeah, it's undefined.
Yeah, I typed that in about 10 times before figuring that out. I thought that there was an issue.
Yep.
Cool, that's the answer.
I just like making fun.
Let's see, for number 4, you should get an error message. Does that sound about right? And then 0.34 for number 5. And then when I did 6, I got a scientific notation, like -5.0000, but you had E on the end of that. So we got 3.5. How'd you type it in?
I definitely might have messed it up.
Well, if you have that power of 2, remember you got to bring it out on the outside. Watch your parentheses again.
Hold up. Yeah, look up his phone. Derivative on
Oh, I think I missed a parenthesis.
Okay.
I think I squared the wrong. You're probably right. I'm gonna be feeling
Try it again.
Yeah, I will try it.
Let's see, for 5, if you got 0.34, that's a positive value, so f of x would be increasing. What about for number 4?
It didn't work.
It didn't work. So this again is representing your slope, right? If you have an undefined slope, it's a vertical tangent, vertical line. Okay, so vertical tangent, because the derivative is undefined. What about for 6? Horizontal tangent, because your slope is 0. Well, so if you got -0.000005, that's very, very close to 0. On the AP exam, you only have to round to 4 decimal places. So this is would be rounded to 0. Okay? So horizontal tangent, because the derivative is 0. All right, we doing okay with the calculator? Moral of the story, did you get it, Anush?
Yeah, I got it.
Okay. Moral of the story, watch out for your parentheses, okay? So we'll stop there for today because the bell's going to ring in a little bit. And we'll continue with this derivative analysis tomorrow. We're going to dive into some word examples. Everyone's favorite.
Yeah, bring that all.